Next up will be Rebecca Hahn in Chemical and Biomolecular Engineering, speaking on computational prediction of energy materials.
Many of you may have seen the new Blade Runner 2049, a bleak premonition of what our world could look like should we continue to indulge our demand for energy at the cost of environment. By 2049, the US Energy Information Administration predicts a 55% increase in global energy consumption. Energy is the biggest challenge and opportunity we will face in this next century. On one hand, if we want renewables to succeed, we need better ways to store intermittent energy, such as hydrogen storage. On the other hand, so long as we continue to use fossil fuels, and we will, we can improve their efficacy. Better petrochemical separation, natural gas storage, and cleaner emissions through carbon capture and sequestration. I work on a class of energy materials with applications in all these processes. Metal organic frameworks, or MOFs, M-O-Fs, are like molecular tinker toys. By connecting metal nodes together with organic linkers, we can build a three-dimensional framework. MOFs are very versatile. By changing what materials we use and how we build them, we can adjust the pore size and shape, the mesh size, as well as the chemistry, how sticky the net is, to make a net that will catch or store anything we want. In theory, that is. In reality, there are two problems with the simplified view. First, there are countless metal linker combinations, but not all of them will self-assemble in synthesis. It is too costly and inefficient to throw materials together, hoping something sticks. Instead, can we predict beforehand if a certain metal linker combination will work? The second problem is that once we have our material, we need to worry if it will survive exposure to corrosive natural gases. We cannot capture carbon dioxide if our material is slowly destroyed by it. Can we predict how our material interacts with other gases? Both of these questions boil down to stability. Will my material be stable enough to exist? And will it be stable if I let it sit in an acidic environment? My research uses simulation to answer both these questions. Simulations are fast, cheap, and very accurate when comparing two quantities. I make models of what I think structures or reactions will look like, and then I compare the initial and the final systems. Lower energy means higher stability. Like setting a ball on this curved surface, the ball will always roll into a valley. Simulations can tell you whether your MOF is on a hill or in a valley, whether it will be unstable or stable. This is the most intelligent and effective way to develop advanced energy materials to meet the world's rapidly growing need. Thank you.